In questions dealing with friction, it is often necessary to look at both the x component and the y component of the forces. Remember, for every question, we should be doing a free body diagram in order to clearly delineate the x components and the y components. So in this example, you apply a 100 Newton force to a moving 20 kilogram mass. The coefficient of kinetic friction is 0.40, and what is the acceleration of the mass? So here we have a real-life diagram, and we're pushing the box to the right. We can draw a free body diagram. There's a force of gravity going down. Opposing that is the normal force going up. To the right is our applied force, and to the left is our friction force. We're looking for the acceleration of mass, so A equals question mark. Our applied force is 100 newtons. And the coefficient of kinetic friction, because the box is moving, is 0.4. So because we're interested in the acceleration, let's look at the x direction first. F net is our friction force plus our F applied. We can replace F net with MA because we know the box is accelerating in the horizontal direction. Force of friction we can replace with mu Fn, and because it's acting backwards, this is going to be negative, plus our applied force of 100 newtons. We're looking for the object's acceleration. We're given the mass, we're given mu, however, we don't have the normal force yet. So let's look at the y direction now to see if we can find a normal force. In the y direction, our net force equation is Fn, normal force, plus Fg. The box is not accelerating in the vertical direction, so that is equal to 0. Fn, we can substitute Fg with mg, but it's actually negative mg because Fg is going down. We rearrange for Fn. Fn equals mg equals 20 kilograms times 9.81 meters per second squared, and that number is 196.2 newtons. Now we can go back into our x component and substitute that number in for the normal force. Substituting everything else, the mass is 20 kilograms. We're trying to find A equals 0.40 times 196.2 newtons plus 100 newton. We solve for A, and acceleration is 1.076 meters per second squared, or 1.1 meters per second squared to the right. Let's look at an example where the object is not moving and we have to overcome static friction. What applied force is required to move a 8 kilogram chair across a level floor if the coefficient of static friction is 0.30? So we're looking for the applied force. Mass is 8 kilograms. And our coefficient is 0.30. Here we have our free body diagram. Acting down is the force of gravity. Acting up is our normal force. To the right, let's push the chair to the right, is our applied force. And to the left is our static friction force. Because we're looking for the applied force, and the applied force is the x direction, let's look at the x direction first. So F net is F app plus the force of static friction. The object is not moving, in fact it's not accelerating, therefore we know F net equals 0. We need to supply just enough force to overcome static friction. And at this point, there is no acceleration. The object is about to begin to accelerate if we apply more force, but it's still not accelerating, so F net equals 0. So we have 0 equals F app plus the force of static friction. We can substitute the force of friction with mu Fn, and this will be negative because Ff is acting to the left. However, we don't know what Fn is, but we can look in the y direction to figure out what is Fn. So let's look at the y direction now. Fn net equals Fn plus Fg. The object is not accelerating vertically, so that's 0. 0 equals Fn plus mg, but it's actually negative mg because gravity is acting downwards. So now we can write Fn equals mg, which is 8 kilograms times 9.81, which is 78.48 newtons. That is our Fn. Now we can go back up here and substitute. And we can rearrange for F app at the same time. So F app equals mu Fn. F applied is 0.30 times 78.48 newtons that we just figured out from our y direction. So then our F app, once we calculate this, is 23.54 newtons, or 24 newtons to the right. Let's now look at an example where the applied force is applied at an angle. A bulldozer pushes down on a 100 kilogram cement block with a force of 300 newtons at 20 degrees to the horizon and does not move. What is this force of static friction? Let's draw a real-life diagram. We have a cement block, and imagine if we have a bulldozer pushing it down. Okay? So in our free body diagram, we have our force of gravity going down, normal force going up, and there's an applied force in that direction. And it tells us it's at an angle of 20 degrees, and acting to the left is our frictional force. Now remember, frictional force always acts parallel to the surface between the object and the ground. And because the surface and the ground is horizontal, our frictional force is horizontal. Okay? We are asked to find what is the force of static friction. Now because the force of static friction is in the x component, let's look at the x component. F net equals the frictional force, static frictional force, plus F applied. However, we must note that this is only the x component of our applied force, because if we have an angle force, we can break it down into its y component and into its x component. And if you remember from earlier, to find the x component of the force, we will need to use the cosine function. The block is not moving, in fact it's not accelerating, so F net is 0, and we can find the frictional force. 0 equals F of Fs plus F applied is 300 newtons times the cosine of 20. We solve for static friction. It is 282 newtons, negative. It is negative because it is acting to the left. In this example, our y component is not required because we have all the forces and all the information necessary in the x component. Let's now try an example where we change perspective. Our surface is no longer a horizontal surface, but a vertical surface. How hard do you have to push a 1.5 kilogram book against the wall if you don't want the book to move? Let's draw a real-life diagram. Here we have the wall, here's the book, And imagine if you have a hand pushing against the book. And in our free body diagram of the book, the force of gravity is going down. You're pushing on it. That's your applied force. Our normal force, we normally draw a normal force straight up. However, the normal force is always drawn perpendicular to the surface. And because the surface, in this case, is vertical, our normal force will need to be horizontal. And here, the normal force is acting to the left. So what is holding the book up? What is acting against gravity? Oh, it is our friction force. Friction force, if you remember, acts parallel to the surface. And because the surface is vertical this time, the friction force is vertical and it's acting up. Okay, now that we have drawn a free body diagram, let's list our other variables. We have a mass of 1.5 kilogram, and we are told that our coefficient of static friction is 0.50. And we're looking for F applied. Now, because F applied is in the horizontal direction, let's look at the horizontal direction first. F net equals Fn plus F applied. It's not accelerating in the horizontal direction, so that is 0 equals Fn. We can actually substitute Fn with Ff divided by mu, because if you remember, the force of friction is mu Fn, and if we rearrange for Fn, it equals Ff divided by mu. So we can substitute Ff divided by mu for Fn, but now we're substituting, so we check for signs, and because Fn is acting to the left, this should actually be negative, plus F applied. We are given mu, but we do not know Ff. So therefore, let's look in the y direction to see if we can find the force of friction. In the y direction, F net equals Ff plus Fg. We don't want the book to move vertically, so there is no net force, so that is 0 equals Ff plus force of gravity. We can substitute with mg. Once again, this is negative because the force of gravity is acting down. So now we can solve for Ff. Ff equals mg, which is 1.5 kilograms times 9.81 meters per second squared. So our force of friction is 14.72 newtons. Now we can take that value and replace it where we see Ff in the horizontal direction. So 0 equals 14.72 newtons divided by our coefficient, which is 0.50, plus our Fap. And we're looking for Fap, so Fap equals 14.72 newtons divided by 0.50, which is equal to 29 newtons. And it's positive because we need to apply the force in the right direction. So here you have it. You can actually hold the book up against the wall, not by applying a vertical force, but by applying a horizontal force. The normal force applied through the wall will also affect a frictional force holding the book up against the wall.